First speaker this afternoon is Shailesh Chandrasekaran, and he's going to tell us about interacting massless Dirac fermions with spin charge flip symmetry.
Hi, Simon. I hope you can hear me.
Yeah, I hear you perfectly.
Great, thank you. Okay, so I would like to first thank the organizers for giving me this opportunity. I've learned quite a bit, and it's the subject that is very close to my heart. So, of course, I see giants in the field here, so my contribution is going to be pretty minimal, but hopefully a bit provocative. So let me see if I can get some conversation going. So the talk I'm going to discuss was done in collaboration with these authors. I will talk a bit more about that collaboration in a minute. And of course, we are funded by these agencies. Let's see. Okay, here we go. So the work is done by mainly two young people. One is Hanqing Liu, who is my student currently. Hopefully will graduate next year. So if you're looking for somebody really strong, please consider Hanqing. Many of you already know Emily Huffman. She was my former student, right now a postdoc at Perimeter. So Hanqing did most of the analytic calculations and some numerical work, which I will not be able to talk about here in the Meron cluster approach. But Emily was sort of the powerhouse to do all the fermion bag calculations. And of course, many of you may know Ribhu Kaul, who is a well-known condensed matter theorist. And I think his insights into this project, especially this notion of spin charge flip symmetry, has been very important and in fact leads to many of the things that I'm going to talk about. Okay, so here is sort of a brief outline of the talk. I will present a quick motivation as to why we are doing what we are doing. And then I will spend some time describing the lattice models that we are trying to use and why, right? And we have this new idea of doing calculations using what I call fermion bags. And so that then motivates the model. And I'll explain to you why. And then I will talk about what the symmetries of our model is. And then in some sense, see how it embeds itself into a continuum, because this is an important thing to understand phase transitions and understand how the various critical points can be described by. And this is something that has been very interesting to us. And this is where the spin charge flip symmetry will play an important role. And then I will present some continuum analysis that I just mentioned was done by Hanqing. And then I'll present some Monte Carlo results that Emily has obtained, and then present some conclusions. So there's actually a poster by Hanqing Liu, if you had a chance to look at it, which discusses these two. And then I think some part of Emily's poster also mentions about our Monte Carlo results. Of course, it's already perhaps too late for you to go back to looking at this poster, but if you get a chance, I would definitely urge you to do that. So let me begin with the motivation, right? So we all at this workshop learned that fermions in 3 dimensions or 2 spatial dimensions are really rich. They have a whole bunch of new fixed points that we'd like to understand their properties. And so it's a rich area of physics, and we are just learning about it, I would say. Although it is a very old subject, I still feel there's a lot for us to learn here. Of course, there are lots of analytic work that one can do. Maybe the bootstrap is one approach which perhaps will give us a lot more information. But on the other hand, there are also many perturbative approaches which give you a good grasp on how we might be able to understand some of these critical points. However, at the end of the day, maybe we want also some non-perturbative methods. And we do have Monte Carlo methods, at least for a class of these problems, but they are very difficult to access. And the difficulty comes from 2 parts. One is, of course, the fermion sign, because whatever model you write down, perhaps it has a sign problem and it's very hard to calculate. On the other hand, even when the sign problems can be solved, Monte Carlo methods are not very nice, especially when there are fermions, because as you explore large system sizes, you encounter difficulties, and typical calculations only involve, I would say, a very small number of points. Now, there have been calculations in this workshop that have been reported on large lattices, but my understanding is that they're still not at the critical point. So yeah, it's like maybe QCD, where people can go to very large system sizes, but as the quark masses become smaller and smaller, you go to the real critical point, let's say the continuum limit, things really become very difficult. So what we have been doing is exploring sort of a new method, which we call the fermion bag approach. And then the question is, what can we do with that? And long ago, I proposed another method, which I call the Meron cluster approach. These have very different ways of doing our analysis. The algorithm works differently. And so the question is, can we use these methods to go to much bigger lattice sizes? And I will explain to you how this comes about a bit. And then, of course, the question is, what can we learn from them? So that's sort of the main motivation to what we are doing at the moment. So let me briefly mention about the lattice models, right? Unfortunately, I would say the fermion bag approach or the Meron cluster approach is rather restrictive, right? You cannot do your favorite model, at least at the moment, the way one could do using maybe auxiliary field approach or hybrid Monte Carlo, even the sign problem is solved. That goes with this idea of efficiency, right? So you have to write down models which are naturally encoded in variables such that you get space-time regions, which we call fermion bags. And these fermion bags are then easy to update. So an interesting class of models that we can do calculations with are of this type. So this model is important to us, right? So it's basically like a model of nearest neighbor hopping. But unfortunately, instead of just having a C dagger ICJ plus C dagger JCI, which appears as a free fermion term in all lattice models in the Hamiltonian approach, we exponentiate this, right? And there's a coupling alpha. This eta ij are, for this work, we are going to choose eta ij to be the pi flux phase, if you a pi flux model, right? Alpha is a constant, which is one of the couplings, if you wish. And omega is another, just a scale, right? It sets the scale for the Hamiltonian. So the model has one tuning parameter, right? This, if you think sets the scale, you can change alpha naturally, right? When alpha is very small, you see that this is almost like a free fermion, you exponentiate it. So when alpha is small, you basically are close to the fermionic, a free fermion fixed point. And then as alpha is tuned, we get into some interesting phases. And that's sort of the physics we'd like to understand for these class of models. In a more familiar set of terms, for example, for NF equals 1, this model is basically what we call the TV model. And so that then tells us what alpha should be in terms of T and V. And these are the alpha and omega related to T and V in this simple way. Right? When V equals 2T, notice that this diverges. So alpha actually becomes infinite, but that's just a coordinate singularity. The Hamiltonian is still very well defined. And in that limit, one can actually use the fermion bags actually nicely become Meron clusters. So this is a class of models where when alpha equals infinity, the algorithm is extremely fast and efficient. But then, of course, that's not the place where all critical behavior occurs. You have to change alpha, and then you can still maintain efficiency and do the calculations using fermion bags. Now, in this in this model, I will call this as the bond operator, right? Because this is basically a nearest neighbor set of couplings. If you exponentiate it out, it's not just a free term. It also couples with itself. And so you can think about it as some kind of, in a very naive way, a current interaction, but it's not quite, right? We will discuss the symmetries as we go on. So now, why does this structure actually help, right? If you think about the reason why the structure helps is, let's write down H as a sum of bond operators, which I call HB, and then write it as some free plus interacting term. It's just that the free term is just 0, and this bond just becomes the interactions, right? And then I can use the usual partition function in the expansion, if you wish, in some kind of a Dyson series. And this has been explored by many authors in the past. This is usually called the continuous time method, right? And then this trace for this particular model, since H0 is just 0, is just a inserting a bunch of interactions, and the interactions are a sum of bonds. So then you sort of take a set of bonds, right? HB1, HB2, and so on. And then have a configuration of bonds. And these bonds are all time ordered in some interesting way. And then you integrate over all time. So you can actually do this calculation in continuous time. There's no need for going to discrete time, although I will flash some results with discrete time. The main interesting feature is that this HB is now an exponential, right? It's exponential of a free hopping term. And that makes it very nice, right? So now if I go back to the partition function, I can use what is called the BSS formula, which is always used in the auxiliary field approach, and write this as a determinant of 1 plus a multiplication of many, in fact, K of spatial by spatial matrices. Right? And this is exactly what happens in the auxiliary field approach. Except that in this fermion bag approach, each of these B1s are a very simple spatial by spatial matrix. Remember, it only acts on nearest neighbors. So it's actually identity everywhere except for a block, right? A 2 by 2 block, which labels the 2 nearest neighbor sites. And that structure is very helpful to create the fermion bag concept. So in the traditional auxiliary field method, this B is very non-local because it can talk to many lattice points. And so that makes it much more inefficient in calculations. So for example, let me quickly explain the fermion bag idea. You basically start with your partition function, right? And think about this B field. If you wish, there are a bunch of bonds, nearest neighbor bonds at various times, right? And then if you think about what is happening, the fermions are coming, let's say from some t equals 0 time slice, and then they entangle themselves with the neighbor, right? And then these become some kind of a bag, right? And then it goes forward and this gets entangled with this part. And if there were only these bonds, then only these 3 fermions entangle themselves, right? Similarly, these 3 and these 3, and maybe this fermion is never entangled, right? Of course, when beta is small, you can expect some things like this, right? At high temperatures, you will naturally split your lattice into many block diagonal terms in this matrix multiplication. And these are what are called these fermion bags. So the determinant is naturally block diagonal. Now you might say at very small temperatures, of course, all these bags will merge with each other. And that's always a case of for fermion bag approaches, because there are some limits where the fermion bags sort of merge. At that time, typically there is a dual formulation, but in this case, I will not get into that discussion at the moment. So let's say in this case, the temperature is very low, so there are lots of bonds. Everything has gotten mixed. But then if you look at a very high, some kind of a finite time slice, then again, I'm sort of exploring in that region some fermion bags. And so when I do updates, I can still use this idea of fermion bags and only update sort of big regions in space-time, right? So that's sort of the advantage. Now, of course, at the end of the day, all of this doesn't really give you a new scaling of the algorithm, as we pointed out in another paper, but it's just much faster, right? And so, at least for small lattices, we can reach, or I would say for lattices up to some big lattice, we can reach reasonably easily. So these results were published last year. So for example, we did the first calculation was in an NF=1 model. We used the continuous time formulation. And these were the results that we obtained for some correlator, let's say some correlation function of 2 points, which is basically an order parameter correlation function, right? And in a broken phase, we expect this correlation function to saturate as it's happening here. And in the for small alpha or small v's, we get a free fermion theory, and that's where it starts going down like a power of 1 by L to the power 4, right? And then at some intermediate temperatures, intermediate couplings V, you get some kind of an interesting power law. And from that, we can actually explore critical behavior. And here is a plot of our critical behavior. And the largest lattices we could use were 64 squared. And so remember, beta equals L. So we are doing actually low temperature calculations. And so you can think about it like some kind of a 64 cube box in 3 dimensions. These were our critical exponents that we got from our calculation. The critical point was somewhere close to 1.28. Of course, we also did this calculation using discrete time, because somehow remember that the fermion bags had an advantage when we could keep the time slices big. So in a discrete time formulation, we could actually do the calculation faster. And so here is the same model, but in a discrete time approach, right? And we do get back the same critical behavior in these discrete time approach. Now we were able to reach up to 100 by 100 lattice sites at really low temperatures. Again, beta equals L. And again, the critical exponents match. In fact, what we realized is that although we were at discrete time and go to bigger lattices, the fluctuations actually in our problem were bigger compared to the continuous time. So the error bars are actually, unfortunately, bigger. So this bigger lattice really doesn't help, I would say, in terms of reducing the error bars. At this stage, I'd like to make a caution to people who are doing small lattice calculations and extracting critical exponents, right? So this is an important thing for us to keep in mind. And this is, I think we learned quite a bit from our calculation. So here, I plot two results, our calculations in sort of 2 different regimes. Basically comparing with previous work of the same model. For example, as soon as this model was known to be solvable, we solved the sign problem. Matthias Treuer and his group came by and looked at it on very small lattices, right? Only 225 sites totally, right? Something like 15 by 15 lattices. And they did an analysis, and their critical point was at VC of 1.304. Remember, the real VC is 1.28. And they got a critical exponent of eta of 0.3, right? And knew of that. And then after some time, the group of Hong Yao came by and did slightly bigger lattices, right? 1,000 sites. And they were able to show that the critical point actually moved slightly, right? And that the critical exponents changed significantly, right? And remember, we should compare this with our values on much bigger lattices, and the drift is now clear, right? Now, of course, one might say we have to go to much bigger lattices before everything converges, and that's always an important thing to keep in mind. But just the cautionary statement here is, when we do calculations on a small lattice, and I think we all know this, here is a sort of a clear example of how things can drift as we make the lattice sizes bigger. Okay, so then the question is, okay, so these are just a quick results of what the various exponents are. So now notice that the NF equals 1 calculation, these are the continuum calculations with various kinds of methods. Compared to ours, there's definitely convergence here in this approach, right? So this is what we would like to expect. Now, this in this workshop, I learned that we also were able to fix this anomaly in the bootstrap approach. That was nice. So the question is, we would like to extend the success to a different model. So we now want to think about the NF equals 2 model. So let's quickly think about the symmetries of our model and then see how they are embedded in the continuum. So the symmetries of the lattice model, remember, are exactly the same as that of the free lattice Hamiltonian, although it is interactive, right? So one might ask, what are the symmetries of the lattice model, especially the free lattice model, which is just obtained by just this term, right? Because there's just an exponential of that. And so we know the usual symmetries that are independent of NF, that comes from just simple translations on the lattice, right? There are 2 directions, there are 2 translations by 1 unit. Then there's, of course, lattice rotations, there's parity, there's time reversal, and then there's charge conjugation, which is related to particle holes, right? So these are, I would say, the discrete lattice symmetries that are independent of NF. But then with NF, of course, there are continuous symmetries that emerge. So I'm going to focus on NF equals 2. So there is, of course, 2 layers of fermions, or in condensed matter language, is just the spin. So there is spin rotation. But then in condensed matter, we also know on a bipartite lattice, there's another symmetry, which is basically pseudo spin or charges. So there's an SU2 charge symmetry. In fact, these 2 together form an SO4 symmetry of the theory. Now, in addition, our lattice model also has a spin charge flip symmetry, because we are in free fermions, right? So we can always make a particle hole transformation on a single layer, and that then converts a spin to a charge, right? So there is a spin charge flip symmetry. So the internal symmetry of our theory seems to be O4. I told you that this becomes SO4. And then, of course, there's a spin charge flip, which adds an extra Z2 and makes it O4. So the phase diagram of this theory, in fact, we had numerical evidence of it. So we were sort of interested to know how this symmetry breaking occurs. And what we have evidence is that for small couplings, alpha small, close to the free fermion fixed point, we have, of course, massless fermions. And then one of these, either the spin in the form of an antiferromagnet or a charge in the form of some kind of superconductivity, one of these 2 breaks, not both, and the spin charge symmetry breaks spontaneously, right? And this breaks, of course, to a U1. So we get either an antiferromagnet or a superconductor in the high coupling constant side. And then one might say, well, this is like a usual chiral Heisenberg of the Hubbard model type, but not quite, because of the spin charge flip symmetry, right? So this is where it was useful to compare with the Hubbard model. So the Hubbard model, the U term, the n minus a half up times n minus a half down, breaks the spin charge flip symmetry, right? So this Z2 is gone. So you only have an SO4 symmetry. Now that SO4, of course, breaks in the usual way, right? So in the Hubbard model, you have an SO4 symmetric phase with massless fermions, and then you get a massive phase with antiferromagnetism, right? In our model, it looks almost the same, except that this is O4, and the spin charge flip symmetry is also spontaneously broken. And so this phase looks very similar to what one might expect in the antiferromagnetic case. But does that mean we get the same critical exponents or not? So that was the interesting question. And this is where Ribu came by and suggested that this is most likely different. And so, especially in many cases, the spin charge flip symmetry is not considered in condensed matter, whereas it's very natural. Remember, we're just doing free fermions. So this must be part of the free fermion theory. And so this O4, not SO4, the O4 must be part of the free fermion symmetry. So we wanted to then understand how all this fits in. So the question was, does the symmetry, of course, we all know that symmetry and their breaking patterns determine the critical behavior. The question is whether the spin charge flip symmetry changes the critical behavior. So then we wanted to understand how one can embed these lattice symmetries in the continuum. And this is where Hanqing's insight came by, right? So he looked at the free fermion in the continuum, right, with two flavors. So this is something that I had known for many, many years, has a U2NF symmetry, which is what I had learned. But then we realized that in the lattice, if you think about how this comes about, in one way, here, for example, I'm choosing 1, 2, 3. 1 and 2 will be spatial. 3 will be temporal, right? This is the Euclidean time. These are all 4x4 Dirac matrices. So we are having two Dirac flavors of fermions here. We can choose gamma 1 and gamma 2 to be purely imaginary, right? And then since they're all Hermitian, they will be anti-symmetric, right? And so then there are three real matrices, gamma 3, gamma 4, and gamma 5. They'll be symmetric. And so if you then work out, actually the symmetry of this theory is not U4, but O8. And this is something that I was quite puzzled by. And apparently in condensed matter, this is a very natural way to think about the symmetry. And the way to think about it is to think about not psi bar and psi, but to think about Majorana representations. So just write psi and psi bar as real and imaginary Grassmann fields, and then try to look at the properties of these gammas, and then you'll see that there is a nice representation in which gamma mu actually, this object becomes some kind of Dirac, 2x2 Dirac matrices times a unity. And so actually you get 8 Majorana objects with an identity in between. So it's naturally in O8 symmetry, right? So the U2NF is actually embedded in this O8. And for us, the O4, all the lattice symmetries are actually, we should think about it as being embedded in O8, right? Of course, O8 times all the other space-time symmetries, which of course, this has the usual Euclidean rotations and all that. So the O4 actually is very natural in these Majorana representation, and it's just these 4 Majoranas rotating among themselves. With that understanding, we can then go back and look at how all the symmetries are embedded. The lattice symmetries are embedded in the continuum, right? And Hanqing came up with various kinds of bilinear terms. So there are apparently 36 mass terms, which was also discovered earlier in this work by condensed matter theorists. And then he says that there are also 28 current terms, which I still have to verify, but I've begun to trust Hanqing in some of these calculations. They are pretty robust. So clearly there's a whole bunch of 4 fermion coupling constant space. Hanqing says that there are actually 5 independent Gauss-Nouveau couplings one can write down, and then to study the flow diagram in that 5-dimensional space would be a very interesting thing. But for the moment, we have only done a 2-dimensional calculation, as I will show you in a minute. So to make some progress, we have looked at Gauss-Nouveau models which have our symmetry breaking pattern, which either breaks the spin or the charge, right? So we were looking at mass terms, which are like the spin mass terms, which basically are anti-ferromagnetic terms, right? Or the charge superconducting terms. So there are 3 of them, 3 of these S's and 3 of these C's. And so one can now do a continuum analysis of these various things, right? And so what happens is you start with a free fermion and perturb it with 4 fermion couplings, which preserve our lattice symmetries, right? The SU2S and SU2C. In fact, you can also show that these models are O4 invariant as expected, because these form the naturally 4x4 and antisymmetric matrices in this space of Majorana, 6 antisymmetric matrices, 4x4, 6 antisymmetric matrices in the Majorana language. And then, of course, in the spin charge flip symmetry language, GS and GC have to be equal. And the question is, what is the role of that symmetry? So first we performed a mean field analysis to see if we get the symmetry breaking pattern that we actually get, right? So we want massless fermions for small couplings and the broken phase where one of these symmetries breaks, right? And so here is an effective potential calculation in this one loop effective potential. These dark blues are the lowest places in the potential. These yellow are the highest places, right? So we can see that there are 4 minimum, right? And these are the magnitudes of our vectors. And so either the spin is broken or the charge is broken, right? So indeed, the spin charge flip symmetry is broken and one of the SU2s is broken. That's the way the symmetry breaking pattern arises. So let's do the renormalization group analysis. So we've actually done a whole bunch of analysis here all at one loop, and I'm sure there are experts in this audience who might either have done it before or may be able to do it much easily than us. So remember that we want to understand the fixed point when GS equals GC, but we did a calculation in general, assuming GS is not equal to GC, obtained the one loop beta function, and we find 4 fixed points in this case, right? And so the 4 fixed points, I'll just talk about the 2 plus epsilon results given the time. So this is the free fermion Gaussian point, right? Then this is the usual Hubbard fixed point. And remember, there are either the spin or the charge. There are equally symmetric fixed points there. And then here is the new spin charge symmetric fixed point, right? So when GS equals GC, we are flowing along this line. So initially we'll see a massless phase, but then when we go to a critical coupling, we'll get into a broken phase. And this is this phase where both the spin charge flip symmetry is broken and the one of the spin or the charge sectors is SU2 is broken to U1. So we calculate the critical exponents at leading order. I'm not sure if this is so helpful because this is just at leading order, but still they are different from the Hubbard model as we expected. So just to make a comment, if any of you know another calculation, we have looked at the literature, we haven't found this discussed, but if it is there, please let us know so that we'll be aware of the literature. So here are some Monte Carlo results from Emily, right? So the first thing we looked at was just the antiferromagnetic correlation function, right? So this is just the SZ component of the antiferromagnet with the oscillating phase, right? So we look at the 2-point correlation function at the midpoint of our lattice, right? And what do we expect, right? As L becomes large, remember for every L we can calculate this object, and L becomes large, in the massless phase, it should go like 1 over L to the power 4 because they are basically a 2-point correlation function of 2 bilinears, right? So essentially it should go like 1 over L to the 4. In the broken phase, since it's antiferromagnetic order parameter correlation, it should go to a constant as I pull the 2 apart. At the critical point, we expect it to go like 1 over some power, and that power is typically represented as 1 plus eta, where eta is one of that critical exponents. So let's see what we get, right? So here is the data. So we have done calculations up to 48, L of 48. These are the 3 different V's. At V equals 1, notice that we are, it starts dropping fast. So if I actually try to fit to this form, this is a straight line on a log-log plot, I get a power of 3.32, right? Of course, it's not critical in the sense that most likely it'll keep bending, and then at some point it becomes sort of like a free fermion, but that could be at much larger lattices. And this is something that we usually observe in the massless phase. Now notice that this power is very different from 4. It is roughly 2.1 or 2.2, right? And then of course at smaller v, bigger v, we start seeing some kind of saturation. Okay. So indeed, we are going from an anti-ferromagnetic phase to a massless phase through some critical point. And so one could argue that maybe the rough critical point up to these lattices, remember this is a very good power law fit, is roughly 1.52. Now in the critical region, we have done a lot more, we've got a lot more data in all of these various V's, right? And of course, as usual, yes.
Shailesh, you've had 35, so you've got 5 plus 5.
Great, thanks, Simon. I think it should be fine. So in the critical region, we have looked at all these various couplings. Remember, the critical value was at 1.52, where the power was 2.16. We looked at 1.50, and there the data started falling off at L equals 48, and now it was a good power law fit so far, but then the power law is beginning to change here. So we believe that maybe the critical point is between these two. Here again, the power law is a very good fit where the power is 1.99. So remember that the power is 1 plus eta. So that suggests that at least if it is between these 2 points up to these lattices, we're going to get more data here. So we think that the eta is roughly between 1 and 1.16. But of course, this is all, again, I already cautioned you against taking small lattice calculations. Here we have L equals 48. But again, I would say we should still take it with a grain of salt. But and so that's the numbers we have. So what I did was just did a rough critical scaling analysis, assumed that V was 0.67. Actually, the data does, if I take all the data from L equals 16 to L equals 48 in some region, it's a reasonably good nonlinear fit, which of course has its own bag of worms. But then we get an eta of roughly these values, eta, nu, and the critical VC. So if I choose the VC to be this, and then plot this, it sort of seems to fall on some reasonable universal curve. So these will be sort of a preliminary set of critical exponents. And I think Emily has the technology to really push this further into larger L's. We just need a lot of computing power as usual. At the moment, we've used exceed resources with 400,000 CPU core hours, by the way. So you should compare this with other large scale calculations. I've heard that to be going into millions or even tens of millions, right? So hopefully we should be able to do a much better job if we can get more computing power. So I also want to give you a sense of the spin charge flip symmetry being spontaneously broken. To do that, we have looked at an order parameter that is invariant under spin and charge, but is odd under the spin charge flip symmetry, right? And that is naturally, so we can again look at a correlation function of that order parameter, and that is naturally the Hubbard coupling, right? So we can actually add the Hubbard coupling in our model and actually study the Hubbard transition also. But at the moment, we've just used it to measure the 2-point correlation function. And this is odd under spin charge flip, but it's invariant under spin and charge transformation. So again, we expect this in the broken phase to go to a constant if the symmetry is broken, right? And so indeed, here is some preliminary data in that, right, for this particular correlation function. And we do see that it's sort of beginning to average at 1.60, which is in the broken phase. Okay, so that's all I had. So hopefully I was able to convince you that there are lattice models with interesting physics that are suitable for fermion-back calculations. But these lattice models typically have a spin charge flip symmetry. We can, of course, break the spin charge flip symmetry if you want to, but the spin charge flip symmetry leads to new fixed points, right? And these are not the ones that are obtained when we add the Hubbard interaction. So it's a new opportunity to learn about some critical behavior in these models. So our model shows actually that there is indeed a nice quantum critical point that is governed by this new fixed point, at least to the lattices that we have done. And the phase transition between the semi-metal and an antiferromagnet or a superconductor, which is accompanied by this breaking of the spin charge flip symmetry, can actually be studied using our model. So an analysis up to L equals 48 gives you some rough estimates of the critical coupling. Thank you.
Thank you, Shailesh. I'm going to applaud you on behalf of everyone here. We have time for questions. So Shailesh, I would like to ask, I mean, I'm very interested to see what you said. Is there any possibility that there's any relation between this this new interaction that you're looking at and something like the current interaction of the Turing model, which, as you know, I've always believed is also profoundly different from the Hubbard interaction?
Yeah. So I think Hunching is sort of the now expert in our group about that. So his belief is that whenever we write down these kind of lattice interactions, usually we get all kinds of couplings, not only the Gros-Nouveau coupling, you also get Thirring couplings. And so a more global analysis of all flow in this multi-dimensional space is what is important before we will know where exactly we are flowing to. So some kind of fine-tuning would be necessary if we want to really study the Thirring coupling. But I would say the naive coupling is sort of a mixture of all possible couplings.
And I don't know whether Holger or Lucas was next, but I'm going to pick Lucas because Holger's an organizer.
Sure.
Holger was first, but I take the chance. No, I forgot my question. No. So I guess the question was, I mean, this fixed point, this new fixed point, you expect that it has a different symmetry, right, than the Hubbard model fixed point. So it has 08 symmetry, is that right? Or what's the symmetry of the fixed point?
No, so remember the Hubbard model only has an SU2 spin and SU2 charge, but there's no flip.
Mm-hmm.
So our model has an extra Z2 symmetry. That's all is more in some sense. But that extra symmetry is sufficient to create this new fixed point, as I showed you in this flow diagram, right? You are on that axis, and in that axis, there is another fixed point. So typically, one would study something on the x-axis or the y-axis. And that's also a flow, right? You can just be on that axis and you will not generate so if you start with the spin interaction, you'll not generate the charge. If you start with the charge, you'll not generate the spin. And so there will be fixed points there. And I believe that is what is the fixed point that typically people study when you study the Hubbard interaction. But now what we are saying is that when the spin and charge are symmetric, there is a new axis goes in the middle, and there is a fixed point there, right on that.
Yeah, okay, I got that. Yeah, thanks.
Holger.
Yeah, thank you, Shailesh. So referring to this fixed point plot and that fixed point out there, it seems to me that the perturbative computation, it looks like it has two relevant directions, but you were able to fit your data, your critical data, to just, I mean, the standard exponents, nu and eta. Should there be some sort of fine-tuning to really stay on that, I mean, to be able to fit that to exponents?
Not quite. Remember that axis is very special. That is the spin charge symmetric axis. So if your model, lattice model respects that symmetry, you're guaranteed to be on that line. So we don't need any extra tuning, but you're completely right. If I now break that symmetry, there are two ways to break it, right? Either with a positive U or a negative U, like in the Hubbard model. If I break it with a positive U, I flow to the antiferromagnetic fixed point. If I break it with the negative U, I flow to the superconducting fixed point. And so this symmetry, I think, was known before, but it's just that the Hubbard interaction with a particular U picks one of them. However, our lattice model is still interacting and we can be on that axis, right? So typically, that was sort of the new insight that Rebu gave us, right? So typically when condensed matter physicists think about it, they break the symmetry and think about it as an antiferromagnet. However, from a theoretical perspective, we can be on that symmetry and we can then explore that axis. So you're completely right. So if we didn't have that symmetry, we'd have to tune more to get to that symmetry. But since our lattice model naturally has that symmetry, no more tuning is necessary.
We just have time for a quick question from David.
This is a closely related question. Maybe I missed it. So did you write down a Gros-Neveu-Yukawa type description of this fixed point involving fermions interacting with scalars in a Lagrangian?
Yes, so we did two kinds of calculations. One was 2 plus epsilon, where we could do the calculation without a Yukawa thing, but Hanqing has done the calculation with the Yukawa also, and we get the same physics. And in 4 minus epsilon, that's more natural, right? And so that's what we have done.
How many scalar components are there in this description?
So there are 6 scalar components, 3 for the spin and 3 for the charge.
Okay, so it's like sort of 2 copies of
vectors.
A Gros-Neveu-Yukawa Heisenberg coupling,
right.
And they're related to each other by a Z2 symmetry?
Right, exactly. So the natural way to write it, once you write it in the Majorana language, it's very natural. There'll be 6 mass terms. You just couple the 6 mass terms to the 6 scalar fields in the Majorana language, and then you write down your scalar things as usual.
Okay, thank you.
Thanks, and can we thank Shailesh again for a really stimulating talk?
Thank you.
Okay, it's now time to move on to our next speaker, Simon Catterall, who's going to bring it all home with symmetric mass generation in lattice gauge theory.
All right, let's see. Mode. Okay, can everyone see that?
Yeah, perfect.
All right, very good. Yeah, so I'm gonna, first of all, I'd like to thank the organizers for such a sort of stimulating and sort of interesting meeting, and thank them for giving me the opportunity to talk to you here. So I'm gonna talk about some new mechanisms for generating fermion masses. These kind of have arisen basically from the condensed matter community over the last few years. And I'm going to sort of talk a little bit about how they might be applied in the context of particle physics and particularly lattice gauge theory. Some of these ideas also have a parallel development coming from formal quantum field theory, and I'll mention that as we go along too. So here's the plan for the talk. I'll tell you what I mean by symmetric mass generation, on this idea of generating fermion masses via interactions without breaking symmetries. And we'll see that some of the constraints on that relate to these things called Hooft anomalies. So I'll remind you what Hooft anomalies are and how they're linked to this notion of symmetric mass generation, or how they form basically boundary conditions on when you can do symmetric mass generation. I'll talk about anomalies, particular anomalies in the context of Kähler-Dirac fermions. And we'll see that the discussion really runs the same whether one's on the lattice or in the continuum. That's one of the advantages of Kähler-Dirac, is that you can forge a very close connection between the continuum and the lattice, particularly when it comes to things like topology. And it turns out these anomalies, of course, are topological in origin too. And I'll use that as a sort of stepping stone to talking about some numerical results. Some of these numerical results are now almost 5 years old. Some of them come from Shailish's work. In fact, he was the one who started along this path. These relate to staggered fermions, which are related themselves, as you know, to Kähler-Dirac fermions. So and we'll talk a little bit about 3 and 4 dimensions there. And then finally, I don't know whether I'll have time to get to this. This was my original goal, but I'm not sure we'll get there. I'll show you how most of these interactions are implemented via scalar fields and Yukawa interactions. And in the last part of the talk, if I have time, I'll show you some very preliminary results which indicate that you can generate some of these same phenomena using purely gauge interactions, so renormalizable interactions. So as particle physicists, we tend to like that better. So I'll get to that if I can at the end. All right, so fermion masses, let me just start off with a sort of general statement. I mean, typically when we think about fermions and mass, we think about breaking symmetries. So you can do this explicitly. If you write a Dirac mass term down, of course, you've explicitly broken axial symmetry. You know that it can also happen in a spontaneous fashion. So for example, the chiral condensate in QCD is another way in which fermions can ultimately end up with masses by spontaneously breaking symmetries. And of course, there can be more exotic scenarios like the eta prime mass, which arises because of anomalies. So in all cases, though, symmetries are broken basically as a consequence of fermions acquiring mass. And you might say, well, is that always necessarily the case? Does that exhaust all the possibilities? And the answer is no. There are actually no-go theorems that stop fermions acquiring masses without breaking any symmetries at all. But that doesn't mean it's easy to arrange. In fact, you have to make sure, and that'll be one of the take-home points from the talk, is that all the Hooft anomalies associated with all global symmetries in the system have to vanish for you to be able to gap fermions without breaking any symmetries. And so this is what symmetric mass generation is all about, basically finding a set of interactions and a fermion content which allow you to cancel out all the possible global anomalies in the system in order to have a chance of building fermion masses into the system via interactions. And we'll see it's restrictive, but there are certainly examples, and some of those examples have been even seen numerically at this point using staggered fermions. All right, so let me give you, first of all, I'll just start off in the continuum and remind you what we mean by Hooft anomalies. Okay, so let's just think about an SU5 gauge theory with a single global U1 symmetry G. All right, and we'll take just chiral fields, left Weyl fields. We'll take a 10 and a 5 bar, okay, the chi and the psi, and they have charges 1 and -3 under the U1, right? So this is basically the Georgi-Glashow theory. It's a gut theory from a long time ago, but it gives us an interesting place to start the discussion. All right, so this is the chiral gauge theory. That means I can't write down an invariant mass term, but nevertheless, the gauge anomaly cancels. So the anomaly coefficient for 5 dar is just minus that of 10. And so it's a consistent, or potentially a consistent quantum field theory. So what do I mean by a Hooft anomaly is I imagine now weakly gauging this global G symmetry, all right? So I know how to compute the anomaly for that global, if I was to gauge the G symmetry, and I would just sum up the cubes of the charges. So in this case, I have a 5 bar with charge -3. So I have 5 times -3 cubed. And then I have 10 fields transforming with charge 1. So that gives me a 10 times 1. So that comes up to -125. So if I was to gauge the U1 symmetry, this is basically the anomaly coefficient that I could compute in the UV, all right? So the point is that if I do this, anomalies are basically RG invariants. So if I compute the anomaly in the UV, it has to be the same in the IR. So it has to be -125 in this case in the IR, just from this U1 symmetry. Now, the only things that can give rise to anomalies are massless particles, right? Usually massless fermions. So one way in which you can make sure this anomaly is satisfied in the IR is to have massless fermions in the IR. And those are going to be composite fermions because this is a confining gauge theory, right? So there have to be some sort of composite massless fermions in the IR, which can saturate the anomaly. Or I could spontaneously break symmetries, and then I would get Goldstone bosons, and those also can satisfy the anomaly in the IR. That's basically what happens in the case of QCD. That's the argument for why chiral symmetry has to occur in QCD, is because there's no other way to satisfy the 't Hooft anomaly, which would follow from weakly gauging the flavor symmetries in QCD, say SU2 cross SU2. So those are the only two options, basically. The 't Hooft anomaly has to be, if it's there in the UV, it has to be there in the IR. And there, you have to arrange your particle spectrum in order for that to happen. Oops, what's going on now? There we go, it's just slow. All right, so there's one obvious color singlet you can write down in the IR, and it just corresponds to coupling the 10 to 2 of these 5s. And so you can just count the charges, and this thing has U1 charge minus 5. And then you notice that's remarkably exactly what you need to get the minus 125 you computed in the UV. So in fact, in this model, it's believed that in fact you can satisfy the 't Hooft anomaly by having composite massless fermions, all right? Because they automatically satisfy the 't Hooft anomaly mechanism, all right? So so it predicts, if you want, that this composite fermion, there's 3 fermion here, remains massless in the IR. All right, and so that's what's meant to be believed. So this is the usual statement about how 't Hooft anomalies work in the continuum. To get to symmetric mass generation, you just do a small twist on this picture. If I want to make all the states massive in the IR, then the anomaly must vanish in the IR, because I can't get anomalies from massive states. That means I have to cancel the anomaly in the UV too. All right, so how can I do that? Well, the simplest way in this model to cancel the anomaly in the UV is just to add a singlet with exactly a charge of plus 5. Then if I add up the sum of the cubes of the charges again, I get exactly 0 in the UV, and that's then consistent with 0. That leads to 0 in the IR, and that's consistent with the existence of a massive state, because then I can just couple this composite fermion xi bar to this new singlet I just wrote down, this SU5 singlet, just using, if you want, a Dirac mass term. All right. So in other words, this is an allowed completely symmetric mass term I can write down in this theory. And if you expand it out over the original elementary fermions, it's just a 4 fermion term. All right. So this preserves all the 't Hooft anomalies in the system. And so this is one way in which I can gap all the fermions potentially in this theory. This is not proven, but it's believed to be the case, by simply starting off with a fermion in the 5 bar, the 10, and a singlet of SU5. And then I can couple them together with a 4 Fermi term and generate fermion mass without breaking any symmetries whatsoever, and whilst not violating any of the 't Hooft anomalies. So there's one other additional observation you should make with this, which is that notice I start off with a 10, a 5, and now a singlet. So I have 16 vial fermions to make this work. All right. So that 16 turns out to be significant. So let me try to say a little bit more about that. So this magic number 16, which emerged in the sort of simple Georgi-Glashow model example, can be seen in a more general context. In fact, people have spent some time over the last few years classifying the kinds of a certain set of new discrete anomalies, which when you try to gauge them in the way I did for the U1 symmetry, actually give you constraints on the particle content, on the number of fermions you have. So for example, in 1 dimension, if you have a discrete symmetrical the usual thing, time reversal, you need 8 Majorana fermions in order to cancel all the 't Hooft anomalies coming from the discrete time reversal symmetry. In 2 dimensions, the relevant symmetry is chiral fermion parity. That also requires 8 Majorana or equivalently vial fermions. In 3 dimensions, it's again time reversal, and that requires 16 Majoranas. And in 4 dimensions, it's what's called a spin Z4 symmetry, and that also takes 16 Majorana or vial fermions to cancel the anomaly off in the UV. So that therefore, potentially, you could gap states in the IR. All right. So for example, in the case of this 4-dimensional spin Z4 symmetry, the precise statement is that the number of left-handed minus right-handed vial fermions has to be 0 mod 16. These symmetries are just the natural symmetries that arise in the presence of the 4 fermion term, in fact. So if you think about, once I write a 4 fermion term down, I still have this invariance where I could take the left into minus I times the left and the right into I times the right, and that would actually be a symmetry of the system. And so what's really happening when in our SU5 model is that we're getting constraints on the fermion number because of the presence of this 4 fermion term that gives rise to additional constraints, which which if you need to cancel the associated anomalies off, will lead to a constraint on the number of fermions, basically. So this is work that stems both from the sort of formal QFT community and also from the condensed matter community at this point. So it started off with seminal work by Kitaev about 10 years ago, discussing Majorana modes in one dimension, and then has been boosted up over the last decade in a series of works by a lot of different people, in fact. Okay, now, if you're on the slide for any length of time, it just slow to respond. So let me just say a few more words about how these anomalies are manifested, because it will be useful when we come to discuss the lattice. So the way you think about this is the following. I have some massless fermions, say, I integrate them out, and I get the partition function and some background gauge field, or even just a scalar field. So it's just some field here. If I have some classical symmetry of the action, which takes A into A primed, then I have some sort of anomaly whenever the Z of A primed is basically not equal to Z of A. So in other words, when the partition function is a function of the connection or the scalar field is not a well-defined function of it. As I go around between two equivalent configurations, the partition function changes by a phase. Right. So this is a generic way of actually classifying all anomalies at this point. You could even get the usual anomalies that you're familiar with, like the ABJ anomaly, out of this analysis, out of this construction. So for example, if you think about Witten's global SU2 anomaly, which says you'll have an anomaly with a single vial fermion in SU2, that corresponds to this eta that appears up here being equal to a half. And it implies, therefore, that when I integrate out over the background gauge field, I get 0. So typically when these phases arise, it means the full partition function, when you integrate over the relevant gauge field or scalar field, actually vanishes. All right. So in general, it's hard to compute these etas. There are techniques for doing it, which are related to a construction which goes under the Difreed method, or the Difreed anomaly, Difreed anomalies. And basically what you do, one way to compute these etas is to compute the dependence of the partition function for free fermions on a background geometry. So basically to do, essentially calculate a gravitational anomaly for free fermions in a general curved background that allows you to infer what these etas are, and hence to figure out what the structure of these anomalies are even in the flat space theory, basically. All right. So anyway, from our perspective, the consequences for symmetric mass generation are the following. If you want to gap the fermions in the IR, if you want to produce massive states in the IR without breaking symmetries, you have to make sure that all the anomalies cancel in the UV. The usual gauge anomalies, if you're thinking about a gauge theory, plus any other global anomalies, including discrete anomalies. So that's really the new component. There are anomalies associated with discrete ZN symmetries, which people didn't really consider until very recently. And those give constraints basically on the particle number, if you want to cancel them off. And one method to see those anomalies is basically to compute the partition function, or to examine the partition function on a curved background. And so canceling anomalies just amounts to the fact that Z should be independent of that background. So this anomaly cancellation is certainly a necessary condition for symmetric mass generation, but dynamics is also important. So I'll give you some examples later on where one needs more than just, say, for example, pure four fermion interactions to make things go. And also the structure of and the symmetries of that four fermion interaction can be very important as well. So it's not just a question of counting fermions. There's more to it than that. And that's really where I think a lot of the potential for new work arises. People understand in low dimensions exactly what kinds of four fermion interactions you need. But as you go up to 2+1 or 4 or 3+1 dimensions, it's much less clear what kind of interaction you really need in order to actually gap the fermions. So certainly you need to satisfy these anomaly constraints, but you need to do in general more than just that. All right, so why might a lattice theorist be interested in symmetric mass generation? Well, the primary motivation, I think, for most people would be the problem of formulating a chiral gauge lattice gauge theory. So we know because of the Nielsen-Niemeyer theorem that you basically end up having to start off in your model with some sort of lattice Dirac fermion. And then historically, there have been two main approaches to making progress. you can try to separate the left and right-handed vial modes in some additional dimension. That's basically the domain wall fermion approach, and it's closely connected to, of course, to overlap fermions. Or you can try to separate the left and right modes basically in momentum space and use strong interactions to give, say, cutoff scale masses to the right-handed states, the so-called mirror states. So both of these sort of directions have been pursued historically with a variety of different lattice fermion proposal over the years. In both approaches, you end up having to use 4 fermion operators to decouple the left and right. That's even true in the domain wall fermions in practice. That was the origin of what were called these waveguide models from the mid-90s. Once you put those 4 fermion operators in, you have theories with discrete global symmetries. And what I guess was not known in the old days was the fact that these discrete global symmetries had Hooft anomalies, and that it was very important to, if you were going to succeed in gapping these mirror states, it better be that you satisfy those, you cancel out those associated Hooft anomalies. So if you want, that's why there's some reason for optimism that we might be able to revisit some of the old ideas now equipped with this new knowledge. So what you immediately learn is that if you want to cancel all the Hooft anomalies out in 3 or 4 dimensions, you better start with multiples of 16 Majorana fermions. That's the take home. And as I said before, you know what kinds of, it's not just a question of anomaly cancellation, there's questions of dynamics and phases of the theory to worry about and things like that. And that part is only known really well, I believe, at least as far as I understand it, in low dimensions, stemming from the old work of Kitaev and Witkowski and people like that. All right, so that's sort of a general background to what we're trying to do, or what we should be aware of from the continuum when we try to do symmetric mass generation and lattice theories. So let me now sort of turn to a specific lattice model involving staggered fermions and say a little bit about that. So this is a model that was written down, I guess, originally by Shailesh, as far as I know, about 7 or 8 years ago now, maybe, I don't know. It's about the simplest model you can think of, which has 4 fermions in it. So I start off with single component staggered fermions. I write down the unique 4 fermion interaction, which is just for 4 copies of them. So chi1, chi2, chi3, chi4, there's nothing else you can do. And then I just use the staggered kinetic operator for the fermions. So these are what are called reduced staggered fermions because I only have 1 Grassmann per site, not a chi and a chi bar, but just a chi. And these are the usual staggered fermion phases. You don't even need that for the moment. So this has lots of symmetries. It has an SU4 symmetry. I can rotate them into these fermions into each other. I can shift. This is sort of a translation, discrete translation symmetry. And then there's this Z4 symmetry where I can just multiply any staggered fermion by I epsilon, where epsilon is the parity operator. So that's the site parity operator. And it's very easy to see that these symmetries prohibit all the bilinear terms in the effective action for the theory. So this thing doesn't, the way I've written it down, doesn't allow you to generate mass terms naively, at least in the effective action. So let me just show you briefly what the phase diagram looks like in 3 dimensions. It's very easy to show at strong coupling that you get a 4 fermion condensate as G goes to infinity as I take the Yukawa up. So the fermions are massive. You can show that is consistent with that statement. But this condensate breaks no symmetries whatsoever of the theory. And clearly, as G goes to 0, I just have massless staggered fermions. So there has to be at least one phase transition between these 2 regimes. And this is a picture from one of Shailesh's papers showing precisely what happens at that transition. So this is some fermionic susceptibility. It's like, as a function of U is equivalent to G for me. So it's the Yukawa coupling, basically, the 4 fermion coupling. And you see a nice scaling peak with non-Heisenberg exponents that arises at some critical value of U, and you can do finite size scaling, and Shailesh has done that on actually bigger lattices than this even to derive a set of exponents, and those exponents are definitely not Heisenberg-like exponents. So there's some sort of exotic phase transition with no order parameter, which separating this massless from massive symmetric phase. And it's built from this very simple reduced staggered fermion model. Okay. When we looked at this ourselves, we wanted to do it through Monte Carlo simulation. So we actually replaced this SU4 symmetry by an SO4 symmetry and basically coupled the fermions together to a scalar, a real scalar. in fact, you can reproduce the 4 fermion term we were looking at by just taking, by essentially making the scalar transform under one of the SU2s, which make up the SO4. All right. So the fermion operator is an antisymmetric operator. And because it's a singlet under SU2 minus, that pairs our eigenvalues and ensures we don't have a sign problem. So the eigenvalues from this operator come in quartets, lambda minus lambda because of antisymmetry, and everything doubled up because everything is in a singlet under the other SU2. So the Pfaffian can be simulated with RHMC simulations with no sign problem. That was one of our motivations early on. If you actually want to see a direct transition from massless to massive symmetric phases, you need to, in 4 dimensions, you need an additional scalar kinetic term. So you need to tune an additional operator as well as just the Yukawa interaction. So that's what I said before, that this statement about how many fermions you have in the theory is not by itself sufficient. You also have to worry about symmetries and about additional operators. So this becomes a marginal operator in 4 dimensions. Okay, so you might have expected you needed it anyway to start with, and indeed you do. So here's an example in 4 dimensions. This is work with David, Sheikh, and my student at the time, Numan Bhatt, who's now a postdoc actually in Havana-Champaign just now. He's just moved. So this is basically a proxy for the 4 fermion condensate as a function of G, and you see it switches on at some critical G. Again, there's no symmetry breaking here. And you see an associated peak and a susceptibility. This is, again, a proxy for that susceptibility. It's the number of CG iterations per trajectory. And you see it peaks nicely as the same point where the condensate switches on. So the coupling kappa here is the coupling to that kinetic operator. So if you don't tune the kinetic operator, you'll find there's a very narrow symmetry broken phase in the center of this peak. If you tune kappa to slightly positive values, 0.05 in this case, you can pass directly apparently through a continuous transition from massless to massive. So here's an example of that. So the peak I just showed you is roughly where the question mark is. So I can pass from this massless phase to this massive phase by sitting around G of 1 and tuning kappa up to sit somewhere in the middle there. There seems to be a continuous phase transition here. If I don't do that, then there's this narrow symmetry broken phase that appears. It's actually antiferromagnetically ordered. And that's what you see in the pure 4 fermion model in 4 dimensions. All right, so this is all written up in this paper. But let me just stop for a second and point out something that was observed back in the day, which is that this model, because it has 4 copies of 4 reduced staggered fermions, it actually corresponds to 16 Majorana fermions. So the fermion content, at least naively counted in this staggered fermion model, is precisely one of these magic numbers that I talked about before in the context of continuum anomalies. All right. So the simulations certainly indicate that you can gap fermions in this particular model, providing you have 16 of them, and that's what we saw came from continuum arguments. But you might ask, is there any way I can get at those anomalies directly using lattice ideas? And the answer is yes. And so I said before that some of the continuum calculations basically look at gravitational anomalies for free fermions. And so one can try to do the same thing here. The problem is that you can't use regular staggered fermions for that, because regular staggered fermions only live on torus, basically a regular lattice with a toroidal topology. So you have to generalize them slightly to make this argument. You generalize them to Kähler-Dirac fermions. And it turns out those massless Kähler-Dirac fermions have an exact U1 symmetry, which is just the analog of the U1 epsilon symmetry of staggered fermions. So you can lift that symmetry up to these Kähler-Dirac objects. And you can show that symmetry is anomalous even when you have a finite number of lattice points. In fact, you can show that the partition function of the Kähler-Dirac theory in discrete form transforms by a phase under one of these classical U1 symmetries, where that phase depends just on the Euler characteristic of the lattice. Okay, so it's independent of the detailed structure of the lattice. I can come up with an ensemble of different random lattices. As long as they have the same Euler characteristic, they'll contribute the same phase. Okay, and so actually this is an interesting example of a quantum mechanical anomaly that arises for a finite number of degrees of freedom. So I don't need to, the folklore is always that anomalies have something to do with having infinite numbers of degrees of freedom and being in quantum field theory. This is an example of an anomaly which you can compute quite straightforwardly on the lattice, and it actually survives even when you have a finite number of lattice points. In fact, in 2 dimensions, I can make this hold with 4 lattice points, because it's the minimum number of points I need to get the Euler characteristic right, basically. All right, so let me just give you a very quick introduction to Kähler-Dirac fermions. So staggered fermions that we're familiar with are best understood as a discretization of Kähler-Dirac. The Kähler-Dirac equation is just an alternative to the Dirac equation. In locally flat backgrounds, it just describes 2 to the d over 2 degenerate Dirac spinors. The Kähler-Dirac equation just looks like this. It involves the exterior derivative and its adjoint acting on a collection of forms, p-forms, so antisymmetric tensors. The reason this has anything to do with fermions is the following. When I square d minus d dagger, because the d squared is nilpotent, I pick up just the cross term, d dagger plus d dagger d, which is nothing more than the Laplacian. So this is a natural square root of the Laplacian, but one which acts on forms. All right, it's sort of if you were Dirac, this is an alternative to discovering gamma matrices. You could just have known modern differential geometry and written this down right away. You might say, what's the connection to Dirac? Well, if I take those forms packaged up in omega and use them as coefficients in an expansion over products of gamma matrices in some locally flat region, I can build a matrix fermion out of them. And I can show the Kähler-Dirac equation, that thing I just wrote down, is just the same thing as the Dirac equation acting on this matrix. So basically it gives you, since the matrix in 4 dimensions, for example, has 4 columns, it just gives me 4 degenerate Dirac spinors with the same mass. Okay, and in flat space, it's just fully equivalent to that. All right. The nice thing about Kähler-Dirac fermions, though, is that I can discretize them in a very elegant way, which preserves a lot of the structure of the continuum equation, which is not true generically when you discretize fermion theories. So I can approximate the continuum by some triangulation. It has to be oriented, which is a technical restriction. I can take p-forms, antisymmetric tensors, and put them on p-simplices. That's obvious and natural. And I can replace this exterior derivative and its adjoint by boundary and co-boundary operators, which naturally act on simplices. And I don't really have time to go into this in any detail, but there's a lot of nice formal structure about how this all works. And you can write down a lattice version of the Kähler-Dirac equation, which follows delta minus delta bar minus m times this collection of lattice p-simplex forms. And you can just replace the continuum equation by this lattice equation. You can show this thing has no additional fermion doubling. And the zero mode structure is exactly reproduced by the lattice theory. Zero modes are, of course, important when it comes to anomalies. Right, so that's the key feature. If I take this Kähler-Dirac equation, lattice Kähler-Dirac equation, and I move to hypercubic lattices with toroidal topology, I can just, it's equivalent, it's completely equivalent to the usual staggered equations. All right, the advantage of this structure is it's valid for any random triangulation with any topology. Okay, so it allows us to look at these issues of anomalies in more detail. So I told you this thing had a U1 symmetry. This is what it is. I just flip the sign of the form according to whether P is even or odd. You can show this commutes with the lattice or the continuum Kähler-Dirac equation operator, and it generates a U1 symmetry in the normal way. It looks analogous to chiral symmetry, all right, but it's not quite chiral symmetry. You can show the massless action is invariant, whether you're in the continuum or on the lattice, and independent of the triangulation you pick. Of course, you should, because we're thinking of anomalies here in quantum mechanics, we have to think about the measure. On the lattice, it's very easy to go compute how the measure changes under this transformation. You just get factors of e to the 2i alpha on even simplices and e to the minus 2i alpha on odd simplices. How many? Depends on the number of nodes, the number of links, et cetera, et cetera. It's just a counting exercise. If you bring all those together, you find that Euler characteristic naturally emerges. So it's a very trivial calculation. In fact, I've got a student right now who's reproducing this calculation using continuum arguments, and it's significantly more difficult to do in the continuum than on the lattice. However, it is what it is. And you can see the partition function transforms by a phase, which just depends on the topology of the lattice you're using. Okay. But it's a gravitational anomaly because I change the triangulation. I'm basically changing the background geometry. All right, so if let's think about this for a second. So if I look at the let's formulate my model on a sphere, for example, just a compactification of R4 or R3 or whatever. So the Euler characteristic of even dimensional spheres is just equal to 2. That means there are exactly 2 zero modes for the lattice Taylor-Dirac operator on a sphere. That's true. So the phase that goes along with that, therefore, is e to the 4i alpha. So this gravitational anomaly in the lattice theory, this dependence on the topology of the lattice, breaks this exact U1 symmetry down to Z4, right? So, but remember, when each one of these Taylor-Dirac fields, like a staggered fermion, tells me it is a way of packaging 4 Dirac fermions together. So I can take this Z4 symmetry of the Taylor-Dirac partition function and use it to argue that now I have to have 16n flavors of Dirac theory in the flat space limit to make this, to cancel out this gravitational anomaly. So one guesses that symmetric mass generation should be possible using 4 fermion terms built from 4 flavors of Taylor-Dirac or staggered fermions, just like we saw in the numerical example, in fact. All right. Actually, this isn't quite what we talked about in the continuum. In the continuum, we said it was 16 Majorana, and now I've just proven to you using a sphere that it should be 16 Dirac. So can you find an extension of this argument that gives the 16 Majorana directly? The answer is yes. I can use a domain wall-like setup where I take my original space and extend it in an extra dimension. So I take my original Taylor-Dirac operator and extend it in 1 dimension using this gamma operator, this linear operator I talked about as the relevant, if you want, gamma matrix in the extra dimension. You can show this thing localizes so-called reduced Taylor-Dirac fermions on the boundaries. This is very similar to the way chiral fermions are localized out of the usual Dirac equation in a normal domain wall setup. So these reduced Taylor-Dirac equations just are projectors. They're just projections of from 1 plus or minus gamma, just like the chiral gamma. And so one ends up with boundary modes, which have a small mass because of the overlap of the wave functions between the 2 boundaries. It vanishes exponentially. But each of these yields 4 Majorana fermions per bulk Taylor-Dirac field in the limit that LD+1 goes to infinity. So I can come up with a domain wall construction, which I've applied the same anomaly arguments will produce the 16 Majoranas that I saw in the continuum and I saw with the numerical simulations of staggered fermions. All right. So it all kind of ties together. So just to summarize where we got to so far, how much time do I have?
Simon, you just about up to 35. So you've got 6 plus 5 to go.
I might get through most of it. All right, so let me just summarize what I've said so far. So generalizations of staggered fermions have gravitational anomalies. That is, they can depend on the topology of the background space, but you can compute them exactly in the lattice theory. When you cancel off all of these anomalies, as you would in the spirit of canceling all Hooft anomalies, as I talked about at the beginning, to achieve symmetric mass generation, that will actually give constraints on the number of fermions, and those constraints are exactly consistent with what you get from these continuum arguments, which I didn't go into great detail, but they exist. So then you can ask, well, can I use Taylor-Dirac or staggered fermions plus this idea of symmetric mass generation to gap out those mirrors and talk about chiral lattice gauge theories? Do I need to use domain wall constructions, or can I do it directly in the bulk? There was one effort in that direction just recently in this paper here. I won't say any more about that right now. I want to go on to one other topic, which is my second bullet point. Everything I've talked about so far is implicitly used basically Yukawa interactions to do the gapping, to generate the mass terms. Of course, that's an irrelevant operator, and you might worry about whether that's a legitimate thing to do in 4 dimensions. So the question is, can you actually replace those 4 fermion operators by some sort of renormalizable gauge interactions? And so I'll just show you a little bit of work with my student, Göksu Kantoga and Newman again on this in the context of the SO4 model. So this is something which is very preliminary, but I'll just show you what it looks like. So I can take my, I can consider a model which is based on staggered fermions still on a hypercubic lattice, and I let those staggered fermions transform under 2 SU2s, a left and a right SU2. That's going to be my SO4 I had before. And I'll put a 4 fermion interaction into play just like before as well. And if I impose this reality condition that psi dagger is sigma 2 psi transpose sigma 2, You can satisfy that exactly if you write psi as a function, as a basically a linear combination of these 2x2 matrices sigma A, which are basically like these guys, the unit matrix and I sigma 1. And you can just show this action just completely collapses to our old SO4 model with this as an ordinary difference operator. So I can take this is just a rewriting of our SO4 model if I impose this reality condition. Okay, and you can check that. Here's a scan as a function of the 4 Fermi coupling of the condensate, and it goes through a transition at just the same place as before. The advantage of this formulation is now I can gauge the delta mu. So I can, in fact, just gauge the SU2 plus, one of the SU2s under that. Yeah, I can just take the covariant difference operator and replace it by a gauged covariant difference operator, basically. And what I can hope to do is generate an effective, strong 4 Fermi interaction in the infrared, even for vanishing values of the Yukawa interaction. So I'm trying to get my 4 Fermi operator not from a strong Yukawa interaction, but from confinement, basically, in the gauge theory. So you can do that. It's easy to gauge that. Here's the gauged action you would need to do, where V is an SU2. And here's a little picture showing you on these very small lattices, but sort of, it's intriguing. This is very early work yet, but as I fix the Yukawa interaction at some small value. This is not enough to generate a 4 Fermi condensate ordinarily. And then I just go down in beta H to strong coupling, and I find a switch on of the same 4 Fermi term we had before. So we can generate that 4 Fermi term and hence fermion masses just now through this strong SU2 gauge interaction. You can see what the phase structure looks like. So around about the same place, the Polyakov line kicks up, corresponding to deconfinement because my box is now too small. Or I can measure the string tension and you see it goes to 0 in the same region. So that all makes sense. I would parenthetically note that in fact, this SU2 model with fermions in the fundamental actually has an exact center symmetry. So the Polyakov line is actually a good order parameter in this case for deconfinement. You can check that there's no symmetry breaking in the system, and that all goes through. So as I add an external source, which would break here the shift symmetry of the action, I can imagine doing this for different volumes, driving the external source towards 0, and you see that the link vev just goes smoothly to 0. There's no sign of spontaneous symmetry breaking. The same is true for the site bilinear, in fact. So we believe that this is an example of a model which can generate fermion masses dynamically due to strong gauge interactions in the presence of a small Yukawa term, which basically is like seeding the mass term for that Dirac mass in the original model. All right, one thing I didn't point out and I should do here is this: if I write down any bilinear term here involving psi dagger psi, it vanishes identically. So this model has no mass term. It can't form a condensate of psi dagger psi because that vanishes identically just by the Grassmann nature of psi. So the best it can do is go through this 4 Fermi channel. If I go to strong coupling, this is what this gauge theory does. It condenses the 4 Fermion operator and hence thereby gives fermions a mass apparently without breaking any symmetries. So I'll move on and just summarize because I'm sure I'm running short of time. So symmetric mass generation allows fermions to acquire masses without breaking symmetries and leads to new phase transitions for strongly interacted fermions. And I showed you an example of that in 3 dimensions with this staggered fermion model, and also in 4, where the phase diagram is more complicated, but it still has such a direct transition, apparently. And so there are plenty of examples of these. The major take-home point from the talk is that if you want symmetric mass generation to happen in some model, you have to make sure you canceled off all the Hooft anomalies, right? And you're familiar with Hooft anomalies associated with continuous symmetries because that's covered in the textbooks. You're less familiar with canceling out Hooft anomalies for discrete symmetries. All right, so that's where the recent work has been, both in the condensed matter literature and also in the formal QFT literature. There are magic numbers of fermions in different numbers of dimensions that make this go. You can get those numbers by actually computing gravitational anomalies in the continuum, and you can even do that on the lattice in the context of Kähler-Dirac fermions. So Kähler-Dirac fermions know about those continuum gravitational anomalies, which is kind of remarkable in a way, particularly since scalar Dirac fermions don't have a well-defined chiral symmetry, right? They have this symmetry gamma, but it's not strictly a chiral symmetry. It's a sort of twisted chiral symmetry. Nevertheless, they seem to know about these same numbers. It's possible that using these new ideas and use to generate masses without breaking symmetries, you might be able to make progress on a very old problem in lattice gauge theory, which is the chiral fermion problem. There's no model yet that does that, but there is some hope, I think, that may be possible to make progress in that way. The standard methods for putting these interactions into gap fermions use 4 fermion interactions or Higgs-Yukawa-like models. This recent work with Newman and with Guksu may be indicating that it's possible to circumvent this using and actually use gauge interactions to do this. So we'll see if that continues to be true. But at the moment on these very early work on small lattices, that seems it's encouraging anyway, I would say so far. So thank you very much. I'm sure I've gone over, but I'll stop there. Thanks.
Thank you, Simon. We have time for some questions. Shuja. Oh, you're clapping, sorry.
I should go back to, I wanted to get people's faces.
I mean, just a quick. So I'm just clarifications. I'm guessing this chiral fermion method you're referring to goes back to Eichten and Preskel and those very old papers. Is that right?
Right. So people tried to gap these mirror states out using 4 fermion interactions back in the day, right? And you know, there were lots of papers written at the time by a variety of people saying this wouldn't work after the initial proposal. One of the reasons it certainly wouldn't have worked was if you have the wrong number of fermions. So most of the numerical work that was done back then would violate these ideas of canceling out all these Hooft anomalies. So from a modern perspective, they shouldn't have worked. But so that's one reason why you might be more optimistic about revisiting some of those old ideas like Eichten, Preskel, or even the domain wall sort of constructions from Kaplan and Neuberger and all that sort of thing. That, you know, even in the domain wall fermions, you do need to, in the end, add for something like multi-fermion interactions in to actually gap out the mirrors. Because the walls are finite separated, you have to do more than just use the domain wall construction.
Kurt has his hand raised.
Yeah, thank you very much, Simon, both Simons. This is a very clear talk, and it just resonates with a long ago problem, costless, soulless phase transitions in 2 dimensions, right? And I was under the impression that the 2-dimensional nature and the strong infrared, the insingularity in propagators prevent the breaking of the symmetry consistent with the no-go theorems, but produce massless fermions. And I was under the impression that doesn't hinge on the representation of fermions.
So I think you can try to make arguments in the context of, say, a Higgs-Yukawa model of what, and in fact, we did this a couple of years ago, that maybe one way to interpret what's happening here is that you get topological defects associated with, the scalar field that you introduce in the Yukawa interaction, and condensation of its topological defects is what's restoring the symmetry. But you also need to argue that somehow the kinetic operators in 4 dimensions, for example, are more like quartics. So so you have to argue the leading quadratic kinetic operator is sort of tuned out, and that may be what you're doing when you're tuning this kappa, is you're actually tuning out the leading operator. The next leading operator, depending on the symmetries, can then play a role. And so the paper we wrote associated with this SO4 model used basically Hooft defects to make a similar argument to the Kosterlitz-Thouars one. So it's speculative, but I think that's one way to think about it, maybe from a particle physics perspective. Yeah.
Thank you very much.
Daniel.
Thanks, Simon. Thanks, Simon, for the very nice talk. I was wondering, I mean, you've been working with these supersymmetric theories on the lattice for quite some time. What is your take on, say, what are the chances for getting close to non-trivial critical points in lattice supersymmetric theories? And I know it's a bit kind of not exactly.
It's not completely unconnected, actually.
Because but I think it's nearby. Yes.
It's nearby in the sense that the way fermions emerge in those supersymmetric lattice constructions is as Kähler-Dirac fermions, right? Not Wilson or anything else. So that's how I first came to be acquainted with Kähler-Dirac, was through supersymmetry. Now the model, but I don't necessarily need supersymmetry to make progress here. I mean, the staggered fermion model I told you about in 4 dimensions is not supersymmetric at all, right? It's a much simpler model, yet it still seems capable of generating a new fixed point in 4 dimensions for strongly interacting fermions. So I think that in itself is interesting, independent of chiral gauge theories or anything else, right? That's if that's really true, and it really needs more work to be sure about that. I think that itself is interesting. In terms of supersymmetry, I guess the usual reason you would use, you would think about supersymmetric models is to make some prediction of weak coupling, right?
Or maybe strong, or maybe, test all these realities which people have come up with.
Yes. So in the case of n equals 4, that's really your only option, right? In 4 dimensions is to do n equals 4 super Yang-Mills. And in that case, that's something we are working on. But of course, in that case, it's a good question as to whether there's a phase of that model where you might be able to gap fermions. I haven't actually thought about that, Daniel, in fact. It's sort of a parallel piece of work, but maybe. I think. I mean, it has the right fermion content. So maybe you could deform that theory in some interesting way, which would lead to new fixed points, because I think, it's consistent with the possibility of symmetric mass generation. So I actually haven't thought about it at all. I think you'd have to deform the n equals 4 theory itself, because otherwise you're either in the conformal phase or on the Coulomb branch, where there's explicit gauge symmetry breaking in. That's not what I want to do, but there might be other phases out there in the lattice theory you could access with maybe by deformations that might fit closer to this sort of category of model. I don't know. I haven't thought about it actually, but you don't need supersymmetry here to make any score. It's not important. That's
okay.
I'm conscious oh, sorry, Daniel, please come back.
I found it very interesting that people now look carefully in the Hooft anomaly cancellation conditions, because that in n equal 1 or with supersymmetry, those have been proven extremely powerful to make actually non-perturbative predictions. They are key for all of that.
Okay? Right, and symmetric mass generation is just a twist on those old ideas. Right, if you want to gap everything in the infrared, you better cancel all the anomalies off. It's really just that statement. And the only really new component to this is the fact that in the presence of things like 4 fermion terms, you have these discrete anomalies, which people weren't familiar with, didn't know had anomalies, etc. They were just discrete symmetries, sorry. And so that's kind of the new component, I guess.
Thanks, sir.
We're deep into injury time, but I think Holger has time for a quick question.
Yes, a quick one. So you don't have an order parameter because you don't have disorder order, but you have a parameter, so an expectation value. So can you use that to define a continuum limit, so in the sense of diverging correlation length? And,
you mean in 3 or 4 dimensions? Or it doesn't matter.
Make your choice.
So you're thinking about the staggered fermion model, for example, and let's just do 3 dimensions for simplicity, 2 plus 1. And Shalish probably has comments about this, but I think there is a well-defined phase transition, a well-defined set of critical exponents. So definitely a continuum limit there. I guess the only question might be as to whether that continuum limit has ordinary Lorentz invariance. Because, as I say, you should really think of staggered fermions as discretizations of this Kähler-Dirac equation, and in at least for strongly interacting theories or theories on curved backgrounds, those are not completely equivalent necessarily to Dirac fermions. So you could have a situation where the symmetries are restored as this twisted Lorentz symmetry that David talked about earlier. So the continuum limits may not be exactly the right ones that you're interested in, but this three-dimensional model for certain has a continuum limit. And it's not the usual, it's not in the usual universality classes of, say, Heisenberg models or something like that. I mean, Shalish may have comments about this since he's worked on 3D more than I have, in fact.
I guess we just discussed about it.
I mean, in 3 dimensions, it's not as surprising. You have there are new critical points, new fixed points. In 4 dimensions, it's more surprising, right? Because the density of fixed points in 4-dimensional interacting fermionic theories is pretty sparse in the normal way of thinking about it. So it's even more interesting in 4 dimensions that you might have something like this. But as I showed you, the phase diagram is much more complicated in 4 dimensions, and you have to very much tune to hit the right phase transition you want.
Thank you.
Thank you. Thank you, everyone. And thank you, Simon, again for an extraordinarily stimulating talk.